we start? So, okay. All right. So, before the break, we talked about expander mixing lemma, which I kind of said is responsible for a lot of local to global like phenomena. So you can take some property which is true in neighborhoods, and then because the statistics in the neighborhoods look very close to the statistics of functions or objects globally, you can make these properties true globally. And let me give one simple example of such a procedure, which is called the distance amplification procedure of Allen, Edmonds, and Luby. And I know maybe Swastik and Mrinal will also talk about this later in more detail, but anyway, in some sense, the whole course is about redundancy. So let me do it one more time. So it's a construction, it's a general procedure which takes, which can be used to construct codes with optimal kind of trade-offs or almost optimal trade-offs between rate and distance. So towards the end, Swastik mentioned that if you have a code with relative distance delta and rate r, then delta is at most 1 minus r. And Reed-Solomon codes in particular achieve this, but then the problem with Reed-Solomon code is that the alphabet is very, very large. Also, this sigma is very large. It needs to be polynomial in n or at least equal to n and so on. And this is a procedure for kind of getting the same kind of phenomenon, but with constant size alphabet codes, where the constant is something related to the degree of the graph for some expanding graph, up to so this is what the singleton bound says, and this construction kind of gives 1 minus r minus epsilon for any epsilon, where we'll choose the graph appropriately, and then constant. It depends only on epsilon, but not on n. And I mean, more than the parameter trade-offs, I just want to show how this gives you some kind of local to global sort of phenomenon. So let's start with any code that you want, which, and then let's say we start with some code word of any code which has some distance. It doesn't need to be what we are shooting for. It just, let's say we call this distance gamma. And let's say the alphabet is 2 to the k for, this k is not the same as Swastik's k. So it's just 2 to the k for some small constant k. And we will take this code word and kind of modify this using an expander graph to give a new code which will consist of just kind of modifications of all code words of our starting code done with an expander. And this new code will really have optimal distance properties. Okay? And the modification is not too bad. So you just think of every symbol of this code as sitting on the vertex of an expander graph. And let's just take a bipartite expander graph. So let's think of a bipartite expander graph. Okay. Let's say this has n symbols and we have n vertices on the left. And let's say we have a balanced graph. So n vertices on the left and n on the right. And we will now take this small symbol, a symbol of size 2 to the k, and encode this small symbol with a code on its own. So this is like a very small code. Think of it as sitting on this vertex. Okay? It takes the symbol of size 2 to the k and converts it into a symbol in a space of 2 to the d, or equivalently the space 0, 1 to the d. So k is less than d. D is the degree of this graph, which is already a constant, and so think of k as something smaller. And this is some constant size code which just maps k bits to d bits. Okay? This we will get to choose with whatever properties we want. Small constant size codes, as long as they exist, we can just even do brute force search or find them in whatever way we want. Okay? So think of this C0 as good a code as you like. And what we will show is that the distance properties of the resulting code globally will be like the distance properties of code words of this small code C0 by this expander mixing lemma local to global kind of phenomenon. And here we can say very nice things. So globally we'll be able to say very nice things. And what is the global code word? So every vertex has degree d. Let's think of it as a d-regular graph still, but bipartite, just to make it easier. And now, after this encoding of every symbol, every vertex here has d bits. You took a symbol of size 2 to the k, converted it into a symbol of size 2 to the d, which are d bits. Every vertex has d bits, so it kind of writes down its d bits on the edges. Let's say you fix some predetermined ordering of the edges. So every vertex writes down its d bits. And then every vertex on the right also now sees d bits, right? So and it just collects these d bits into a string of size d. So, and so you get this new collection of n symbols. Sorry, my rectangles are not really rectangles. Still not. Where every symbol is of size d, and the whole thing, it sits in space 2 to the d to the n. Okay. And this is the whole construction. You kind of instantiate it with some arbitrary code word with some positive distance gamma, and we will choose this code word C0 later with some properties. But let's say if this C0 has this property that in this small space of d bits, it kind of realizes the singleton bound. So it can be the Reed-Solomon code, but on d bits. Okay. So Q just needs to be something, okay. The field size will need to be larger if I take Reed-Solomon, but it can be some nice code on d bits. Then we will get the same kind of behavior globally. And let me say why. So when we started, every vertex had a k-bit string. Then every vertex encoded this k-bit string with C0, the same C0 for everybody. And then every vertex had a d-bit string. This just redistributed, and then people here just collected these d-bit strings. No, not the sum, just the concatenation. So it sees these d bits, it just writes them down one after the other. No, so this one, so every vertex has degree d. So if this vertex writes down these d bits on these edges, every edge only has 1 bit, right? And then I collect the 1 bit on every edge here. Other questions? Means it's like a beautiful construction which is very simple but has amazing properties, and let me mention one simple property of this. Okay, so we kind of have this object, and now let's say we want to understand some code word here. Let's call it H. And we want to understand, let's say the distance between two code words, but let's say the distance between H and 0. And for linear codes, maybe as was take, not sure if you said this or not, but it's okay to measure the distance from 0. So just the number of non-zero positions in a code word H. Otherwise, you can think of, actually, yeah, maybe let's just do it more general. You can think of two code words, H1 and H2, and let's try to measure the distance between them or number of positions in which they differ. But when I say they differ, it just means that they differ in any one of the D edges incident on this vertex, because the symbol is the concatenation of the D things. Okay, and now I'm starting with H1 and H2 on the right. I'm trying to count how much they differ. I'll kind of pull them back on the left. So again, I can do this process in reverse. H1 has these D bits sitting on these edges. Everybody on the left kind of can collect the D. So if there is a vertex L, then it sees D bits corresponding to its edges, H1L and let's say H2L. And so if I have bits on the edges written from the right, I can collect them from the left or the other way around. Right? This process can be done both ways. And now, what I want to claim is that actually for most vertices on the left, since L is the name of a left vertex, let's think of this vertex set as L and this is R. So for most vertices on the left, the local distances of H1 and H2 just in this D bit neighborhood are lower bounds on the global distances of H1 and H2 here, relative distances. So there's the fraction of n on which they differ is kind of lower bounded by the fraction of d on which they differ. But the local distances are just determined by the code C0. So if C0 has great distances, then the global code will have great distances. Okay? And let's just see a quick proof why. So let's just say let's look at the vertices L, where the distance is at least, say, theta times d. So the relative distance is at least theta. So let's look at the left vertices L, where locally at least theta fraction of the d edges, I see a difference between H1 and H2. And let's call this set of such vertices S, okay, which have this property. And every set in S has these kind of orange edges on which H1 and H2 differ, and this many of them. And let's look at the right endpoint of all these edges. And let's call these right endpoints T. So I have a set S, which is just all left vertices where I see a distance of theta. And the right endpoints are sort of these edges on which I do see a distance. The right endpoints of those edges are called T. And now let's just count the number of edges between S and T. So I claim there is an easy lower bound. Any suggestions what it is? Can you say it a little loudly? Sorry. Sorry, that's theta, not 0.8, but yeah, that's my bad. It's so you're right, it's theta times d times the number of vertices in S. Thank you. And I claim the expander mixing lemma also gives me an upper bound. Any ideas on what it is? Suppose the graph is an expander, a lambda expander. So let's say, okay, I'm cheating a little bit, but let's say the second eigenvalue is at most lambda, sort of. So can you tell me what the expander mixing lemma tells me? D over n times the size of S times the size of T plus lambda d times square root of the size of S times the size of T. I'm just going to call that n. So this is an even weaker upper bound. Yeah. And now I divide by d times S everywhere. I get that this T over n is lower bounded by theta plus n is something which is sort of, or this will go on the other side and there will be an error term kind of lambda times n divided by size of S. Okay. Now, S is the number of positions where H1 and H2 differ. If this left stuff was coming from some code which has some positive distance gamma, then they will be different in at least gamma fraction of the positions. Gamma can be very small, it doesn't have to be anything optimal. So this will be at least, this will be at most. If I choose lambda to be sufficiently small, this term won't really bother me. I can think of it as epsilon times n. And now, what is T over n? T was the set of the right endpoints on these edges where we know H1 and H2 differ. So if H1 and H2 differ on this edge, in particular, they differ on this vertex. So this will contribute to the distance between H1 and H2. So this is actually less than equal to the Hamming distance between H1 and H2 divided by n, so the relative distance. This term we can basically ignore if lambda is sufficiently small. And this theta is just a local distance. It's just the distance on the left vertex in C0. So if C0 has great distance, this global code has great distance. Okay? And this is what I meant by expander mixing lemma gives us this kind of property that the global statistics in most places look like the local statistics. Okay? And if you kind of work this out, you can prove a slightly stronger version of this statement that using this kind of second moment-like concentration, that the probability over a vertex L on the left, that the local distance in this vertex of H1L, H2L is a lower bound on the global distance plus some epsilon is at least 1 minus epsilon, where think of epsilon as roughly lambda over gamma. So almost everywhere, the local distance will be a lower bound on the global distance. Actually, so and I mean, I haven't told you something about the rate of the code that I'll let Swastik or Mrinal do when they do that, but you can basically choose, there's a simple calculation in this construction that the rate of this global code can also be made to be the rate of this, this small constant size code times some 1 minus epsilon just by choosing this outer code to have a very good rate. So here we need something very weak about the distance, just has to be some constant. But what the expander mixing lemma does, which is the heart of the distance proof, is to reduce understanding of the global distances between H1 and H2 through the local distances. And then actually this kind of things can also be done for other properties, but yeah, this is just a very simple proof which illustrates expander mixing. Okay. Any questions? Yeah. No, please. So lambda by gamma does not, so lambda is, yeah, okay. I mean, so, oh, sorry. I think that is my bad. It's, no. So this is gamma times n. The number of vertices or the relative distance is gamma for the left code. So that fraction of things is gamma, thank you. It's not gamma times n. Yeah, sorry. Other questions? Okay. So this is just one sort of example of the phenomenon that expanders are good samplers, and then they let us reduce understanding global properties to local properties. Let me briefly mention one other kind of result of this flavor, and then Max will kind of talk about analogs for high-dimensional expanders. But we sort of interpreted this as a second moment inequality. We said that if you look at an average just over a neighborhood, then its variance is upper bounded by lambda square. So it's sort of the average over just a neighborhood looks very much like the local sort of a global average. And in fact, the second moment of this sort of deviation of this local average from the global average is upper bounded by something like lambda square times the norm of f. And you can also do this more. So instead of looking at a neighborhood of size 1, if you look at a neighborhood of radius 2, so you sort of look at the averages over all neighbors of your neighbors, then you can get like fourth moment bounds and so on. And in fact, something even stronger. So you don't even need to look at the entire neighborhoods if you just look at walks. So let's say you do the following. So you look at a vertex u. So let's say we have a function f, which is written on all vertices. And for every vertex, there is some value of this function. And now instead of looking at just calculating the global average, we look at u and then some neighbor v1 of u, and then some other neighbor v2, and some other neighbor, let's say v3. So we kind of start from u, look at a random neighbor, then start from this random neighbor, look at a random neighbor of it, and so on and so forth. And it's called a walk on an expander, which I'll talk about more. But there is kind of a Chernoff bound known for this. So if you look at t steps like this and just take an average of the value you see over these t steps, then the probability that it deviates from the global average significantly is kind of grows down exponentially in t. So formally, in a statement due to Gilman, it's that, let's say if you have a function, this time let's say it's function which takes values which are bounded between 0 and 1. And the probability over kind of a sequence, let's say v1, which is and then a neighbor v2, and then a neighbor v3, and a neighbor v sub t, let's say, of this form. So this is called a walk of length t, and we will talk more about it. If you look at the average of everything you see on this walk, versus the global average of f, the probability that this is larger than epsilon is less than equal to some constant times something which is exponential in epsilon square t times 1 minus lambda times some other constant. So, I mean, there are even sharper versions. I'm not stating the precise constants, but expanders can be used to, and this is what drives a lot of de-randomization applications. So if you want to kind of run an algorithm on a lot of sort of independent inputs and see how it performs, instead of choosing these inputs random and sort of independently at random, we saw that expander mixing lemma says that if you want to pick two things independently at random, you could have picked them according to the edges of an expander. And sort of some correlation properties stay the same. And this one is kind of saying that if you want to pick t things independently at random and you want the error to go down, or you want to get a more accurate estimation of some function or some global property, then you could have actually just picked only one thing truly at random and then pick the next one as a random neighbor, then the next one as a random neighbor, and so on. And this still gives you a pretty good estimate. Okay? So this also drives a lot of de-randomization applications. Okay. Let's talk a little more about these walks, and that basically is used as a third kind of definition of expansion. So let's maybe one other thing which I sort of cheat a little bit on in the expander mixing lemma there, I was talking of a bipartite graph. For a bipartite graph, the second largest eigenvalue in absolute value is not bounded by lambda. So yeah, maybe some of you caught that, but yeah, we'll come back to it. I'll talk a little bit about just dealing with bipartite graphs, but the statement I wrote there is correct. I sort of also applied the expander mixing lemma to two functions. One of them was entirely on the left, one of them was on the right. So the statement is correct, but you need to be a little bit more careful when applying it to bipartite graphs. Okay. Any questions? Okay, so let's talk about basically a third definition of expansion, which is in terms of what happens when you do these kind of walks on expanders, or rather what are called maybe diffusion processes, or rather if you start with some distribution over the vertices of a graph, and then you take one step on a random walk, then what are the kind of new things you get or new distributions you get, and how it evolves as you take more and more steps in the walk. Okay, so let's draw a random graph. Okay. And let's still stick with n vertices d regular. And let's say I start with on this particular vertex. So let's fix a vertex, and I'm just going to start there. So let's say I write the value 1 on that vertex. Okay. And now this, let's call it f, which is just 1 on this vertex, 0 everywhere else. Now I do sort of one step of this walk. What I mean is that I will look at a randomly chosen neighbor of this particular vertex. It has d neighbors. And I'm going to jump to one of those neighbors. And now I'll ask you to tell me what is my probability distribution. So now, because I'm choosing this neighbor randomly, we don't know for sure where I'll end up, but there's some distribution. Any sort of ideas on what that distribution is? Right, so just 1 over d. Another way of saying this is that if this was f, then my distribution is, technically I should apply this f here on the left-hand side, but it's a symmetric matrix, and we can do this. So I started with f, which was just 1 on one vertex, 0 everywhere else, and I ended up at this distribution. And now, actually, if I do this again, you can prove this more generally. So we didn't really need to know the fact that this f was 1 on one vertex. It could have been some other probability distribution p. And I would have had another probability distribution a bar of p, because what is the probability that I started at this vertex? Okay. That is p of v, whatever it is. With that probability, I had this particular f, which was 1, right? That was the probability I started at this vertex. And then I got a bar of this particular one with probability p of v. And this is linear, so you can just sum it up over all probabilities in this distribution. And that also proves that this is a probability distribution. It's not too hard to check. Okay. So this can be just thought of as a way of starting with one probability distribution, going to another distribution. And why stop there? So, and now we can ask, okay, what happens as we keep doing this? What does this process look like? And it turns out that, okay, it's sort of as defined, it actually has a nice fixed point. And at least for the kind of graphs we are looking at, it will converge to the fixed point. So first, let me kind of point out what the fixed point is. We already know this. It's also known as an eigenvector because, well, what is an eigenvector? It's so a fixed point is some distribution p, which kind of where you apply this and you get the same distribution. And we already know one such distribution, which is the all ones vector. Maybe if you want to write a distribution, then divide it by n. And so this is a fixed point of this walk. You get back the same distribution. And the spectral properties or the expansion that we defined, which by the way is also called spectral gap, as Max said, we should kind of, that's how we usually refer to it. So yeah. So the spectral gap or the quantity 1 minus lambda 2, which I call the spectral expansion, determines how fast we converge to this fixed point. And let's just see a quick proof, but this is something which also can be used to define expansion. And then all these three definitions are somewhat different when we start talking about high-dimensional expanders, whether lots of, so just like expanders are defined as kind of graphs with some pseudo-random properties, high-dimensional expanders are hypergraphs with pseudo-random properties. And there also you can define some spectral properties. You can define things like how many edges go between, let's say, three sets S1, S2, S3. Or you can define what happens to some natural kinds of walks that you can take on these hypergraphs. And these three lead to three different kinds of definitions. And here, it's kind of nice that all three are related. So let me at least mention what happens to this definition with walks. Okay. It's almost the same proof that we did with the expander mixing lemma. So let's start with any probability distribution P. It's just another function from the vertices to real numbers. And because it's a distribution, it sums up to 1. Another way of saying that in the kind of our inner product, if you take its inner product with the all ones vector, it's 1 over n. The inner product was expectations. And now we know what happens to this as we take one step of the random walk. Because we know what happens to vectors when we, in terms of the eigenvector decomposition. So we have eigenvalues lambda i's and eigenvectors f. This is just we said what happens to any vector, and then where these fi's form a sort of decomposition of this matrix A bar in terms of its eigenvectors, orthonormal. And again, we can, as before, we can separate the first term where the eigenvector is just all ones and the eigenvalue is 1. Sorry. And this, we already know what it is. It's just 1 over n, right? And this is the all ones vector, sorry. This is 1 over n, this is the all ones vector. So this is just the uniform distribution, right? Which is the stationary point we are looking for. And this is just rest of the stuff, which we want to show is kind of some small error. But this is something which we already calculated in the expander mixing lemma. Because these are orthonormal, and we saw that this is less than equal to and actually, we also know what happens if you do this multiple times. So instead of looking at A bar, if you look at A bar to the t, the eigenvalues of a matrix to the power t are just powers of eigenvalues. So you get this. And the tth power of 1 is 1, but everything else goes down. And so you get actually a much better bound. And let's just see what is kind of how small we would like it to be. So lambda, let's say it's the second eigenvalue, which is somewhat smaller than 1, let's say 0.9. So this is growing as 0.9 to the t. And this is e bar to the t. And how small would we like it to be? Let's say, so one common way of measuring the difference between probability distributions is to say that they are kind of, there's a small difference in every coordinate, or rather, we want to say something like summation over all the coordinates is small. So this is the probability for the vertex V coming from our distribution after t steps. This is the uniform distribution. And we can kind of control it in terms of a quantity of this form just by again applying Cauchy-Schwarz. So I mean, maybe the even easy side of Cauchy-Schwarz. So we know that this is just Cauchy-Schwarz, coordinate by coordinate. And so if we can make it somewhat small, let's say smaller than 1 over n, or let's say some smaller than 1 over polynomial n without even getting into the precise polynomial, then we can get this kind of a result. And so essentially t equals omega of, or sorry, order of log n suffices, or rather more precisely t equals order of log n times how small we want to make it, divided by the base of our log, which is, it grows down by a factor of lambda at every step. So how many steps do we have to take is roughly this much. And this is kind of tight because if you have a d-regular graph, then even to see all vertices, forget having a uniform distribution on all vertices, just to see them, you need log n steps, because after one step, you only see d. After two steps, you only see d square, and so on. And if d is a constant, you need log n steps to even see all the vertices. So the diameter of the graph is log n. And in fact, after order of log n steps, you actually get very close to the uniform distribution. So this is another way in which expander graphs kind of help you sample, or this is another more or less definition of expansion, that you have a graph on which the walks mix very fast. And yeah, for high dimensional expanders, all these three definitions are interesting and somewhat different. Any questions? Yeah. Sorry? Here? So the inner product is just the average of the entries of P. And we know the sum of the entries of P is 1. That's our definition of an inner product. It's just expectation. Okay, and now let me say a little bit about how to deal with graphs which are not regular, how to deal when you kind of remove this deregular assumption, which will be necessary when dealing with high dimensional expanders, where we can't always get all the graphs that we are interested in as regular. And that's where this kind of inner product definition will come in useful. So let's maybe so we still want to think of the average degree as constant, maybe not very high. And let's kind of still try to see some of the things that we would like. So kind of going backwards, we define this A bar in the regular graph case as 1 over D times the adjacency matrix. And this is also precisely the kind of matrix which tells us how this probability distribution evolves. So if you want to just kind of average the probabilities of your neighbors, and so after one step, you are uniform over the D things who are your neighbors if you started at one vertex, and then you keep doing this. And if you don't have a graph which is regular, then the number of neighbors for everybody is different. And so a vertex which has degree 2 is kind of spreading the mass over things, over kind of 2 vertices, and a vertex which has degree 5 is spreading it over 5 vertices. And more generally, the matrix you want to look at is D inverse A, where what I'll say what D inverse is. Let me just say what D is. The D is just a diagonal matrix where the entry corresponding to a vertex is just its degree. And so D inverse is a matrix where it's 1 over the degree. And so this just corresponds to the fact that a vertex with degree 5 is averaging things over 5 things. So the denominator is 1 over, it's like 1 over 5. So that's why I have a D inverse for a general graph. This can be used to study random walks in the same way. This can also be used to give a definition of edge expansion similarly. But let's first talk of vertex of the spectral expansion, which is what we've been using. So what we would like in terms of understanding expansion is how many edges cross. So we want to somehow preserve the fact that we are still looking at some uniform distribution over edges because we're trying to count edges. And so, but the problem is if you want to look at a uniformly random edge, that doesn't give you a uniformly random vertex if you kind of look at its endpoint. And what you get is a vertex with probability proportional to its degree, because high degree vertices are more likely to be sampled. But maybe that's not so bad because, well, you are interested in a random edge, so some vertices are going to get more weight when you look at a random edge. And and actually, it's sort of easy to carry over everything we did by just changing the inner product. So we define this inner product in the case of regular graphs. Okay, so now it will matter, but if you give me a minute, sorry, I multiplied on the left with D inverse, but yeah, if you give me a minute, I'll actually define a self-adjoint matrix, so then it still won't matter. So let's think of, in this case, we define the inner product of F in G as expectation over a random vertex, F of V, G of V. In this case, we'll still study very similar things, except we'll change this inner product. With respect, and I'll explain what this mu is. It's just sample a random vertex with some special distribution mu, and then calculate the same thing. Okay. This is also a valid inner product. It's linear in F, it's linear in G. It's sort of, if I take F equals G, I get some expectation of F of V square, which is non-negative, and so on. So it's a valid inner product. It's a valid notion of distance if you try to calculate that. And this mu is just probabilities proportional to degrees. And the sum of the degrees is the total number of edges counted with orientation. So that's this mu. Turns out, if you do this, the following is still true for the A bar that I defined. For any f in G, with this new inner product. So A bar doesn't look symmetric if you just look at it as a table of numbers. But it is symmetric if you really think of it in terms of what it does, and symmetric in the sense that when you take the inner product, if you act on F or if you act on G, you get the same value of the inner product. And this is kind of the right way to extend symmetric matrices to when you're just working with inner product spaces. These are called self-adjoint matrices, as I referred earlier. And everything we said about eigenvalues, eigenvectors actually still continues to hold. We still have an orthonormal basis of eigenvectors. And in fact, it's still true that the top eigenvector is all ones. So at every vertex, I get, if I just look at A times all ones, I get the sum of the values of its neighbors. The sum of the values of its neighbors is equal to D. And D inverse just multiplies that number by 1 over the degree. And so this is still all ones. And the following is still true, that if you look at and again, if you define kind of the Laplacian so the top eigenvalue by the same argument is still at most 1, and the eigenvector all ones is still the same. You can still look at the second eigenvalue, you can still arrange them on the real line, calculate how far is the second eigenvalue from the first, still use it to define the spectral gap or the edge expansion. Okay? And the entire argument still works. Cheeger's inequality also still works, except I have to say what the kind of graph expansion term in Cheeger's inequality is. So let me mention that. Oh yeah, sorry. For Laplacian, I'm using F on. Yeah, thank you. So remember, we defined the expansion of a set as the number of edges crossing from S to S complement divided by D times the size of the set, but this can be written as a set of vertices in S and you sum over their degrees. In the regular graph, all these degrees were D, so you just got D times the size of S. In general, this is the quantity that is defined as graph expansion. This is sometimes referred to as the volume of S. It's still the number of edges incident on S, so it's still the same interpretation. If you pick a random edge which hits a vertex in S, then what is the probability that it escapes S? Okay, so it's exactly the same interpretation. This quantity, the minimum of this over, so now you have to kind of, instead of taking the minimum over subsets of size at most n over 2, you look at subsets of volume, which is less than equal to total number of edges. Half of the total number of incident edges. So, and you still get Cheeger's inequality. You can also get the same kind of version of the expander mixing lemma, but you have to just use eigenvalues or the inner products or Rayleigh quotients with respect to this particular definition or this particular inner product measure. Okay. And this is one simple way to extend everything we did. Nothing really needs to change. You just have to change the inner product. And okay, we have a few minutes. Let me just mention briefly something about the constructions. So I've been kind of saying or assuming that these kind of expanding graphs are sort of, they exist, and that's why we've been using them for different applications. And let's just sort of see what does it mean by good expanders exist? What kind of parameters are we shooting for? And in terms of what is reasonable to assume? So briefly speaking, actually, if you pick a random graph, it's not too difficult to show that it's a fairly good expander. But let's first just make sure what is the comparison target. So we said the second eigenvalue, even in absolute value, let's say, we want it to be small, and there's actually a bound of Allen and Bopanna which shows that the second eigenvalue has to be at least 2 times square root d minus 1 over d minus something which goes down with n. So, and so the best we can hope for is sort of like 2 over square root of d. Okay. And at least when kind of d is a large constant, this is not really a barrier. This just kind of says that lambda is still, we can still think of lambda as 1 over 100 if d is a sufficiently large constant. And there are graphs which actually can even achieve this. They are called Ramanujan graphs. But before we go there, let me just say what happens for random graphs. Okay. So for random graphs, it's, I mean, non-trivial, but not super difficult to kind of get some small constant times t if you want. And there is actually a result of Friedman which shows that for random graphs, lambda is actually roughly this small, plus in this little o of 1 becomes a plus factor there. So plus some small epsilon with high probability, where the probability depends on epsilon. If you just pick a random d-regular graph, this is a fairly non-trivial result, but it kind of also says that you can get fairly optimal constructions by picking things at random. And there are also some weakly explicit versions of this by Mohanty, O'Donnell, and Paredes. And in fact, there's a much simpler version of Friedman's result, which is recent, called due to Chen, Garza-Vargas, Trop, and Van Handel. But let's talk a little more about explicit constructions. So the first explicit construction of expanders was due to Margulis in 73. Gave an example of an explicit graph which is 8 regular and has the second eigenvalue smaller than 8. It's not quite this bound, but smaller than 8. And once we have some gap in the second eigenvalue, we can always amplify it by just kind of powering. So if you look at the square of the graph, so you just kind of look at walks of length 2, then the degree will be 8 square, and the second eigenvalue will also square, right? And so if you do this t times, the lambda will become lambda to the t, and so if you want it to be smaller than 0.1, you just take t to be large enough. The degree d will grow, but that's doable. So there's a later analysis by Geber and Galil which shows an explicit bound, which is, so this is an 8 regular graph with lambda less than 5 times root 2 over 8 using some Fourier analysis over Zn. Okay. And later there are also kind of explicit constructions of Ramanujan graphs by Phillips, Lubotsky, and Sarnak, and also by Margulis, which actually achieve the optimal bound. Sorry. So these are somewhat more complicated constructions, but we do know that even this bound is achievable. And even without this little o of 1, you can exactly get this kind of a bound. And there are kind of a method of constructing expanders called zigzag product. Due to Reingold, Vadan, and Wigderson. Which can take two small graphs which are good expanders and give a somewhat larger graph which is still a fairly decent expander. And you can keep repeating this construction. So you can keep repeating this construction, iteratively construct, again, fairly good expanders with lambda smaller than any reasonable constant that you want, not depending on d. So, I mean, okay, you can get some function of t, but let's not worry about it. So these are also, and these are very explicit in the sense that not only these constructions, you can sort of write down the whole graph in polynomial time, but if you want to write down all the neighbors of a given vertex, you can do that in time which is polynomial in the amount of time it takes to specify that vertex, which is log of the number of vertices. So you can write down all its neighbors in time polylog n. So there can super explicit constructions, which can also be constructed just by starting with some constant size expanders and iteratively doing this sort of a construction. So we do know a fair number of constructions of expanders with very different kind of flavors, but fairly satisfactory bounds in terms of what properties they achieve. And yeah, maybe Max will contrast some of the situation with high dimensional expanders and what we know about constructions there. Okay, let's stop here. I'm happy to take questions. Yeah. Sorry. So Allen-Bopana result is for all graphs. The way I wrote it is, yeah, this is a D regular graph. So this is the D is the same degree for all vertices. Okay. But for any D regular graph, lambda is at least this much. So in particular, you cannot have an expander which gets a value smaller than this. Okay. Other questions? Yeah. Yes. So they actually get this bound less than equal to this particular number. I mean, these are sometimes called weakly. No, yeah. So these are called weakly Ramanujan graphs. So you have a slight. I mean, for the kind of applications I mentioned, it sort of these things are all excellent. But yeah, Ramanujan graphs are defined as ones which actually get this bound. I don't think it gets any constant times root d, right? It's maybe, I'm not sure if you remember exactly what it gets. It's the zigzag product. It's, I mean, yeah, I'm not even sure it sort of, you can get root d sort of, but you can get any small constant times d. So that, yeah, you can get some function of d, but I don't remember that precise function, but it's not in this regime. Yeah. Yeah. Yes, yes. So, okay, so good. I mean, it's a deterministic construction which you can, yeah, kind of write down in polynomial time. It's, yeah, in randomized polynomial time, of course, you could sample a graph and calculate its eigenvalues and check, but you have to do it deterministically for explicit construction. Yeah. Not for these applications, or like, okay, I guess maybe yes. So if you think of some kind of concentrators or extractors or something like that, then, or like maybe, then you want bipartite graphs which are unbalanced. So they're not, I mean, they're kind of regular, but they're sort of, the two-sided degrees are different and you need this imbalance there. Other than that, I don't know of specific applications where you need the degrees to be different. At least, yeah. Sorry?
There's a construction that uses lossless expander with large imbalance. They also give good because linear time devolving.
Okay.
They need highly.
Okay, sorry. Yeah, so yes, that's true. So if you want lossless expanders, then you want this kind of imbalance construction again. And yeah, as Pavel said, maybe for quantum codes, yes. Yeah. Think if you want like this small constant epsilon, you can get exponentially small probability. Okay. I won't bet on exponentially small. I know you can get polynomially small probability. So order root d, you can get exponentially small because it's a martingale argument. For this one, yeah, let me at least claim inverse polynomial, but sorry? Yeah, okay. So then, yeah, a constant probability when epsilon is equal to 0. So, sorry? Okay. Sorry. Okay, that's what you meant. No, so here I'm thinking of random d regular graphs, and that actually does make a difference. So I'm thinking of the degree d as constant. And if you actually pick a random GNP graph in the sense that you pick every edge with probability d over n, then you do get some imbalanced eigenvalues, or you do get, at least for constant d, you do get some weird distributions. So, but if you pick a graph in the following way, let's say you pick a matching at random, and then take another matching at random and take the union of, let's say, d over 2 matchings if d is even. Then this is a graph where every vertex has degree d. And you don't get collisions or multi-edges almost. So this will be a graph where everybody will have degree exactly d. It will be a d-regular graph. And this will be an expander. So it's not the GNP kind, because there the degrees will be imbalanced. I can't really get very good unless d is like at least log n over n. Until that point, I can't really get things. Like d is log n. Yeah. Other questions? Sorry. Okay. Yeah. So I didn't get time to get into bipartite expanders. To say in one sentence, I mean, there's no significant difference. Instead of working with adjacency matrices and eigenvalues, you can work with bi-adjacency matrix, which just kind of have one row for every left vertex, one column for every right vertex, and work with singular values. And then everything is fine. You can write down one function on the left, one on the right, and you can look at the second smallest, or like the second largest singular value. Singular values are positive, so you don't have to worry about this kind of eigenvalues being negative and positive and having two signs. Just work with singular values. Okay? And even if you have different degrees, you just work with some particular kind of inner product on the left vertices, some inner product on the right vertices. Both sides you can choose it with proportional to degrees, and the same kind of arguments work. Okay, that's what you meant. So actually, yeah, so there is a simple way to construct explicit bipartite expanders, at least if you want balanced, you from this construction, where you just make two copies of every vertex. And for every edge uv, you kind of connect it from the left copy of u to the right copy of v, and the left copy of v to the right copy of u. This is called the two cover of the graph. And so you can take any expander and take its two cover, and the singular values of this two cover will be just coming from like the two signs, the eigenvalues of the original one. And so if you have some good expansion bounds, you get the same ones. I'm sorry? Yeah, so there I used a bipartite expander. So there I just needed a regular one. So you can take one of these constructions, just take like a two cover and gives you that.